Okay, in the previous lecture, previous chapter, we've talked about heat and temperature. Now we're moving to the transfer of heat. So it's heat transfer, right? One mechanism by which heat is transferred is called conduction, and you all experience this. You get out of the shower. Let's say there's a wooden floor here and a tile floor. Which of these are you likely to, your foot is likely to feel colder upon? The tile. So you've all experienced this, right? The reason why the tile feels colder than the wood is because the conduction of the thermal conductivity of the tile is higher. So it conducts heat away from your foot faster than the wood does. The wood, in a sense, is a greater insulator, so it does not conduct the heat away as fast as the tile does. Now, conduction is basically because of the fact that, let's say that if my body were warm or hot and this table were cold, and if I put my hand on the table, the vibration of all the atoms in my hand is being transferred. The molecules in my hand, as they vibrate, they then impinge upon, if you will, the atoms of the table. The atoms of the table then start bumping against each other, right? And so the heat is transferred from my hand to the object. There has to be contact, physical contact between the two entities for this form of heat transfer to occur. So that's conduction. Another mechanism of transferring of heat is called convection. In the case of convection, you actually have motion of a gas or a liquid. So the example that I gave you, my hand touching the table, the cold table, there's no motion of gas, right? There's no liquid, there's no fluid, there's no gas that's moving from one place to another. That's simply the vibration of the atoms in my hand that are vibrating against the atoms and molecules of the table, transferring the energy. In the case of convection, there's an actual physical change, motion of a gas or a liquid. You can see an example of convection like this. If you happen to have one of these transparent pots, right, put it on the stove, you got water that's boiling there, drop in a drop of food coloring, and you will see that little drop of food coloring starts moving, right? It'll leave a trail. What happens is you end up with water that's hot, gets lighter, it travels up to the top, and as it travels up to the top, this creates a low pressure which pulls down colder water. So you end up with these circulating currents of water in this case. You could do the same thing in a room, and you'll end up with circulating drafts of air that transfer heat from one place to another. That mechanism is called convection. So convection is the transfer of heat energy in a gas or a liquid by currents in the heated fluid. So here is an illustration. We talked about the fact that as the sun beats down on the land and the ocean, the land heats up more. So higher temperature, the ocean is a lower temperature. Because this has got a lower temperature and this has got a higher temperature, the air above the land gets heated, and the air becomes lighter, so it travels upwards. As it travels upwards, it creates a low pressure zone here, which then sucks in air from over the ocean, so you end up with a breeze. You've actually experienced this when you go to the ocean. You feel a breeze coming off of the ocean, right, towards land, which seems to cool you off. So over here, so the air that went up then ends up coming down here to the ocean, gets cooled, and you create a cycle of motion of air like this, right? This is one of the fundamental mechanisms for breezes and winds and storms and all that kind of stuff. At night, what happens is the ocean doesn't cool down as much as the land does. So the land gets colder sooner at night. So you got 60 degrees. The ocean is warm compared to the land. So in this case now, the air above the ocean, as it heats up and becomes lighter, it travels upwards, creating a low pressure zone, and so air actually flows from the land to the ocean, and you end up with this kind of a cycle, right? So people who have lived by the ocean notice that there is a change depending on what time you are during the day. You can end up with the wind, the breezes in one direction versus another direction, right? So this is an example of convection. The third mode is called radiation. In the case of radiation, there is no physical contact like in the first mechanism, which was conduction. There's no motion of any physical, like matter, no liquid or gas that's moving. However, in this case, there's just energy moving in the form of photons, electromagnetic radiation. And you've experienced this if you have, let's say you've got logs burning in your fireplace and you happen to stand near the logs, right? And you can feel the heat coming off of the logs. Or you open your oven, right? After you bake something, you open the oven, and as you stand there, you can feel the heat coming to you. There's no air moving in that case. It's just the heat that's coming to you is through photons, through infrared rays, which are similar to light waves or radio waves, except they're a different frequency. All three of these, radio waves, infrared waves, and light waves, are all electromagnetic radiation that arise when I take an electron and I bounce it. Right? We've talked about this, have we? I take an electron, I bounce it. I have this feeling of deja vu. Did we talk about bouncing electrons?
No.
We have not. Then it must have been a different class. Okay, take an electron, bounce it once, right? Bounce. It says ouch. Bounce it again. It says ouch. Bounce it a third time. It says ouch. 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 You notice what's happening? Okay, let me do it again. Ouch, 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 ouch. Do you notice what's happening? What happens when I speed up and slow down the frequency with which I'm oscillating, I'm hitting the bouncing the electron?
Higher pitch.
Yep. Extra credit. Right? What happens is, as I increase the frequency of the bouncing, right? It's like if somebody is jabbing you, right, you say ouch, and they jab you more, at some stage you're going to go pretty high pitched. We can do an experiment. You do the experiment and videotape it, right? And you extra credit if you put it on YouTube. Now, as you increase the frequency of the bouncing of the electron, the frequency of it saying ouch goes up. So as the electron is bounced, it gives off an electromagnetic wave. A disturbance in the force, right? So as it gives off an electromagnetic wave, what happens is the frequency of the wave matches the frequency of the bouncing. So as I increase, so all of these are just electromagnetic waves. At low frequency, you would end up with radio waves. As I increase the frequency, it becomes infrared waves. As I increase the frequency even further, it becomes light waves. Increase it even further, it becomes X-rays and so on, right? So if you were to take an object and heat it up, so here's an object heated to 1600 Kelvin. Now we talked briefly about the fact at some stage that degrees Kelvin is it's the absolute scale of temperature, and to go from Kelvin to centigrade you just subtract 273, right? So 1600 minus 273, 273 will give you the temperature in centigrade or Celsius. So ballpark in your head you can subtract 300. So 1600 Kelvin minus 300 will give you 1300 centigrade. So it's about 1300 centigrade. If you take an object, piece of metal, heat it up to 1300 degrees centigrade, it will give off energy. Here's the radiation intensity versus the frequency. It gives off energy with a peak here. Now take the temperature up to 2400 Kelvin, which is about 2100 centigrade. The peak moves to the right to a higher energy, and the total amount of energy that's being given off increases. Heat it up even further to 3200 Kelvin, which is about 2900 centigrade. You can see the whole peak is much larger and is also shifted even more to the right, right? This is why if you take iron and heat it up, you can see that the temperature of the iron initially is kind of dull red. Right? At first it's gray, then it gradually heats up to dull red, then it becomes more yellowish. Yeah, right? Mm-hmm. What's happening is the peak frequency is shifting towards the right. In principle, if you could keep the sharpness of the peak, you could heat it up until it's like blue hot or purple hot, and so on. In principle. In practice, not. So that's what's going on there. So illustration of radiation is, here's a woman with a clothesline or whatever, like tied to the end of the wall. She oscillates the line up and down with a low frequency. You end up with a wave that looks like this. If you increase the frequency of the oscillation, you end up with a wave that looks like this. So here's the higher frequency. That means there's more oscillations per second. Low frequency, fewer oscillations per second. If you look at these and match these to electromagnetic radiation, like the photons that are coming off from metal that you're heating, low frequency, the material is cool. Heat it up more, it becomes higher frequency. Highest frequency, the material is really hot. The hotter you heat the material, the higher the frequency of the photons that are emitted. This is, by the way, is the way that we're able to look at stars and tell what the temperature of the star is. Right? If you ever wonder, you hear people saying that the temperature of the sun is 5000 degrees centigrade, the surface of the sun. The way you tell is by pointing something called a spectroscope at the sun and looking at the frequency of the light coming off of it, right? And based on that you can tell, like that shape that I had showed you in the previous slide. In this slide, we can look at the spectrum coming from the sun and say, hey, there's a peak above here, which is an indication of the temperature of the gases in the sun. Okay, radiation. Now this is counterintuitive. If I had two metal pots, exactly the same material, like say aluminum, you fill it with boiling hot water. This pot is painted black, this pot is totally silver or white. Let's say white, right? Painted white, painted black. Which of these two pots is going to cool down faster?
The white.
Okay, the white. Show of hands for how many of you think that the white pot will cool down faster? 1, 2, 3, 4, 5. Okay. Does anyone beg to differ? 1, 2, 3, 4, 5. Oh no, we have a tie. What are we going to do? It's a democracy. We can't make any decisions if it's a tie. Sorry?
Override it. You're like president of the class.
Yeah, but if I do too many overridings, you all will hate me, and then, or half of you will love me, and the other half will hate me.
Just side with the other half next time.
I'm sorry. That's a good solution. She said, side with the other half next time. Okay, that's funny. Thank you, though. I mean, to me, it seems intuitively evident that the white one is the one that will cool down faster, right? Those of you who said that the black one will cool down faster, why did you pick that choice? That is extra credit. That is a really funny response. I enjoyed it.
I was actually thinking the same thing. I didn't read that first.
Okay. You were thinking that the black would cool down faster?
No, I was thinking that
The white would? Oh, it could be. They'd be same? Okay, that's a third option. I hadn't thought of that. Yes, it could be the same. We miss you?
Well, if the white one's absorbing all the light and the black one's reflecting all of it, the light energy is going to be put into the white one, whereas the black one's going to be reflecting everything away from itself.
So the white one should cool down faster
Yes. No.
because it's reflecting all the light.
The black one should cool down faster because it's reflecting the light energy coming in, whereas the white one's absorbing it because of the color
Oh,
spectrum.
I see. I see what you mean. Okay, so that's assuming that there's more energy coming in. Let's say
Does
that.
that make sense?
Yes. Yeah. Let's say I see what you're saying.
Say that same thing for warming.
What if I were
The
to?
opposite? Then the white one would warm up faster.
Well, no, because
The white
white,
one would cool down slower,
Yes,
but
something to
warm
do-
up faster.
well, white reflects all of. So I got them backwards. White reflects all light, whereas black.
Yes. Here's the thing. We're talking about two different phenomena, right? So I'm going to set up another Gedanken experiment, a thought experiment, to illustrate the difference between what you said and what they're saying. We're going to do the same experiment in a completely pitch black room, completely dark room. So there's no energy coming in from outside.
Okay.
So reflection doesn't matter now. Would it make any difference?
It's gonna be the same. If they're outside in the heat, then I would think the white would be outside. But
Okay. So I think, good point. Extra credit to those of you who have spoken up, right? I love it. Okay. Two different phenomena. Radiation versus absorption. Absorption, I mean, I think we're going on the colloquial knowledge, if you will, the tribal knowledge, that in the summer, what color are we supposed to wear? White, right? Because allegedly, a white shirt will reflect more of the light, so you just blind all the passers-by and to hell with them. But I stay cooler, right?
It's not true.
I don't know. I mean, I mean, from a physics viewpoint, one would argue that's indeed the case. I'd be very interested in seeing if somebody has done an experiment and actually demonstrated it to be true, right? To a first approximation, I say it's probably true, but I don't know what temperature difference. Is it 1 degree?
It's the same thing with like cars.
With what cars exactly?
Darker cars.
Yep.
Supposed to get hotter.
Yeah.
Yep.
And I feel like it's true just from like personal experience. If you get in the darker car, it feels hotter than if you get in the white car.
Why are you black or white shirt?
Okay. Extra credit to you if you can come across anything out there like YouTube, whatever. Somebody has done an experiment where they have measured the heat difference in wearing a black shirt versus a white shirt in the peak of the summer or a hot one. Yes, mademoiselle?
My husband does. He'll wear a black shirt to my son plays football, so he'll wear a black shirt to the games. And he says he's hotter in the black one than wearing a white one.
Okay. Now, if there's some way to measure it, because we'll have to separate out the psychological factors,
Okay.
right? Because we expect to be hotter. It's possible that we like the.
What about like a car experiment? I feel like a t-shirt would be good.
I have a feeling. Okay, the car. I feel that.
Two identical cars, one black, one white, stick them right next to each other, stick a thermometer inside.
Yes, that would be great.
aside from dropping $60,000 on cars, it's not that difficult to make sure.
That's true. Just look around you, find the nearest millionaire in the classroom and see if they can,
Exactly.
right?
Who's paid you?
I'm sorry?
Who's paid you so far?
Who has paid me? Oh, they haven't paid me. Nobody's paid me. Right? Okay, so extra credit if you can find such an experiment, right? So for now, yeah, the odds are that it is on, it's somebody's done that experiment, right? So it has to be exactly the same model, everything of car, same insides, no cloth seat versus leather seat, that kind of stuff, right? Everything has to be identical. Yes, sir.
I was gonna say that like the difference between concrete versus asphalt in the summer, but that's not cooling or warming anything besides the dirt below it, so you wouldn't be not the same.
Yeah, so I mean, there's the color difference, but there's also the material difference and the conductivity difference and all that stuff, right? Yeah, so you can see that sometimes doing these experiments take a little more. It's harder to do in practice than we can. Okay, anyway, leaving all that aside, in principle, if you were to do this in ideal conditions in a physics laboratory, the black pot will cool down faster. It also absorbs faster, and that's an extra credit assignment to you. It heats up faster, not absorbs. I'm not talking about absorption. I'm purely talking about radiation, right? So extra credit to you to research online to see why it is that the black object cools down faster than the white object, and it does not have to do with reflectivity, right? So it's not a valid statement to say that this is less reflective. Okay? So Newton's law of cooling, next concept that we're talking about, is the rate of loss of heat from an object is proportional to the temperature difference between the object and its surroundings. What does this mean? It means that if I have a boiling pot of water, and if I were to place this in ice compared to the boiling pot of water placed at room temperature, the one that's placed in ice will cool down faster. They both start at the same temperature, but this will cool down faster than this, right? In practice, we all have experienced this. Newton just happened to capture it in a law. His name got added to it. So if you had been the first person to capture it in a law and write it down, it would be your name. Right? I know. What's up with that?
Doesn't that at some point it stops and the water won't actually cool down? So now you have melted all the ice, warm that ice, so you have more volume.
Let's say infinite supply of ice.
No.
Right? But you're right. What happens is as you change the environment of your experiment, the results will change. Something has changed about the situation, right? Good point. When you're setting up experiments, you have to be very, very careful to do exactly that, is to control the environment. But extra credit to you for mentioning that, right? Okay, next concept that we're introducing is the greenhouse effect. On the Earth, what happens is short waves from the sun, light waves come in, they get absorbed by the Earth then re-emits lower energy, which is longer wavelength rays. These rays then go out, and some of these rays are then absorbed by the atmosphere or reflected back to the Earth from the atmosphere. This then results in a net heat coming into the Earth, which then will raise the temperature of the Earth in principle, and that is called, in general, it's a greenhouse effect. This is not a comment on the alleged global warming, right? Because just you're probably aware that a significant number of scientists are skeptical of the claims of the global warming movement. Well, I'll just leave it up to you, right? But here, this is just a statement about how the greenhouse effect works. Same thing at home, right? Like in the midst of the Phoenix winter, when it's like totally freezing and it's all like frozen everywhere, you can keep your plants warm by putting them in a glass house, right? And again, light from the sun is coming down through the glass to the flower, gets absorbed, re-emitted as a lower energy. The flower keeps some of the energy and re-emits lower energy light. It's kind of like if I were to pass $100 bills through the glass and put it at the pot at the end, the odds are that, and if I say you can do whatever you want to do with the dollar bills, what will happen is maybe if I were to send like 100 of them, maybe one of them may end up in the pot, right? So it's kind of like, but I said you can do anything. I'm not making any comment about your honesty or absence thereof, right? So, or presence thereof. So same thing. Energy from the sun comes to the flower. It absorbs the energy and re-emits some of the energy, right? Not all of it. So it's like the government, right? Send them $100 and they pocket $98 and return $2 to you. So kind of like that. Again, that I shouldn't have made the statement, but very true. So here's the flower. Here's $100 coming to the flower. $98 get absorbed. $2 go out as a low energy wave, right? And that low energy is so low that it can't get back through the glass. So it bounces around in here. So the net effect is the energy inside the glass house keeps increasing. So that's what the greenhouse effect is based on. Right? Okay. Solar power you're all familiar with. Certain amount of energy coming from the sun per unit area. So 1 meter by 1 meter square, there's about 1,400 joules of energy per second. So this is equivalent to 1,400 watts, right? 1,400 watts is enough energy probably to host like some significant fraction of your energy usage in your house, if you could come up with 100% conversion, right? So 1 meter by 1 meter, like 3 feet by 3 feet, is the equivalent. It could capture 1,400 watts if you have 100% capture efficiency, which we don't. Now, this is applied with solar panels, that is taking the energy coming from the sun, and you can put them. There are different kinds of solar panels, or even like hot water devices and so on, right? Where in solar panels the energy gets converted through photovoltaic devices into electricity or into a voltage that can then be stored in batteries, or alternatively be sent back into the grid, and the grid can then use it as it needs during peak hours and during off, and then they'll give you a discount against your electricity bill. So solar power in general is the energy per unit time derived from the sun. Okay, so to control heat transfer, so remember that, so up to this point we have talked about, when we talk about heat transfer, conduction, convection, radiation, we are talking about basic science, understanding the laws of the universe, if you will. Applied science would be to try to apply it in some way to something real. Then technology will be to apply it into something that you can sell to a customer. So here's an example, a thermos bottle, right? In the case of a thermos bottle, not very common nowadays, right? I don't see people using thermos bottles very much. I suppose if you have babies or something, right? I don't know. But everybody has microwaves everywhere, so you don't really need to. Or if you go skiing, okay, thank you. So a thermos bottle is like this. There's a glass bottle here. There is a gap which is typically evacuated. There's no gases in it, no air. Then another glass bottle on the outside of it. Now the inner glass bottle is silvered on this side. So these three components of this bottle are used to minimize the three methods of heat transfer that we talked about. We talked about conduction, convection, and radiation. So there's no conduction because there's no material contact. This inner bottle can heat up, but it's not in contact with the outer bottle here for the bulk of its air. Just a little bit of contact there, but you can use the thermal insulator, right? But the rest of this, there's no contact between this bottle and this bottle. So you've totally killed conduction. So there's no conduction of heat. You've killed convection by removing the air in between. If there was air in between, then you could have air currents that will transfer heat from here to here. No air in between. So no convection. Radiation, what happens is when this bottle heats up, it can radiate heat. It can give off heat through photons, infrared photons, heat photons, if you will, that will go to this bottle and then radiate out. So you avoid that by silvering the inside. Let's say you silver this side, then the heat that's coming here gets reflected back in. You can silver this side as well, of the outer bottle, the inner side of the outer bottle. So any heat that comes from here will get reflected back to this. And by this, what happens is the food that you put in the inside stays hot, right? That's an amazing invention. Whoever first came up with the idea. I'm completely fascinated by the areas of inventions and patents, like people who just think out of the box, right? It's an amazing area of creativity, both evolutionary patents as well as revolutionary patents. Yes, a lot of very good patents. The best patents in the world are the ones that seem very simple in retrospect. You look at it and say, it's so stupid, it's so easy, I could have become a multi-millionaire, why didn't I think of it? After the fact. But before the fact, it takes somebody who's like totally creative, right? Who thinks outside the bottle. Okay, so we'll end the lecture with that.